Hello everyone. This is the part 2 of Coordination Chemistry Rapid Revision Notes. In this video, we'll start with Valence Bond Theory. According to Valence Bond Theory, we have different structure for different coordination number and hybridization. We'll make 3 columns, one for coordination number, other for hybridization, and next for geometry. First, if we have coordination number 2, then possible hybridization are SP and SD, and possible structure is linear. Means if we have coordination number 2, we have geometry linear. Then if we have coordination number 3, then possible hybridization SP2 and geometry trigonal planar. If we have coordination number 4, then possible hybridization will be D3S, SP3, DSP2 and SP2D. Possible structure, if we have sp3 and d3s, then tetrahedral will be the possible geometry, and if we have dsp2 or sp2d, then square planar is the possible geometry. Then if we have coordination number 5, then possible hybridization sp3 dz square or dsp3 and sp3 dx square minus y square or dx square minus y square sp3. If we have sp3 with dz square or dsp3, then that case tbp geometry will be there. If we have dx square minus y square involved, then in that case we will get square pyramidal geometry. Next, if we have coordination number 6, then we will get sp3 d2 and d2sp3 and d5s. These three hybridization are possible for coordination number 6. If we have sp3d2 or d2sp3, here in sp3d2 it is a outer orbit complex. Outer orbit complex. And d2sp3 has inner d orbital used, means inner d orbital complex. sp3d2 forms high spin complexes and inner orbital complexes forms low spin complex. So for sp3d2 and d2sp3 we will get octahedral kind of geometry, and for d5s we will get trigonal prismatic geometry. If we have coordination number 7, then in that case we will get hybridization sp3 d3 and d2sp3. And d3sp3 or p3d4. These three hybridization possible for condition number 7. If we have sp3d3 or d3sp3, we will get pentagonal bipyramidal geometry, and for p3d4 we will get capped octahedral. Capped octahedral, or we can say capped trigonal prismatic structure or geometry. The next and last condition number 8. For this we'll get sp3 d4 or d4 sp3 or p3 d5. These three hybridization. For this we'll get square antiprismatic geometry and cubic dode octahedral geometry, then bicapped octahedral, bicapped trigonal prismatic, hexagonal bipyramidal. So these are the possible geometry for coordination number 8. Next we will discuss limitations of valence bond theory. It does not explain existence of inner and outer orbit complex, and color of complexes it does also not explain. Then change in properties of ligand and metals, and pairing of electron in presence of strong ligand. So these are the limitations of valence bond theory. Next, we'll start crystal field theory. First, I will draw all the splitting for octahedral complex and square planar complex and tetrahedral complex. So this is the complete splitting for crystal field theory. So the first one, this is the splitting for tetrahedral complexes. State is for free isolated gaseous ion. Then next, this splitting is for octahedral complex. This is for distorted octahedral. And this is for square planar complexes. In case of distorted octahedral, because of John Taylor distortion, dx square minus y square has higher energy. This is the complete splitting pattern for different complexes. Next, we have some relations, like we have to, for calculating CFSC energy, we have relation minus 0.6 into Q. Here, CFSC energy for tetrahedral complexes has formula minus 0.6 into Q. Q is the number of electrons present in E orbital, means lies in dx square minus y square and dz square, plus 0.4 p. P is the number of electrons present in T2 orbital, into delta T plus m of p. Here Q is number of electron in E orbital. P is number of electron in T2 orbital, and m is number of paired electron. It varies in strong field and weak field ligand. Similarly, for octahedral complexes, we have CFSC formula, that is plus 0.6 Q minus 0.4 P delta O plus m into P. Here same, Q is number of electrons in EZ orbital, P is number of electron in T2G orbital, and m is number of paired electrons. Next, we have relation octahedral energy equals to 10 into dq. We can convert octahedral del O into dq by multiplying by 10. Here d is 35 z into E by 4a to the power 5. Q is 2e r to the power 4 by 105, and dq. On multiplying both, we will get 1 by 6 z e square r to the power 4 by a to the power 5. So this is the formula for dq. Next, we can relate tetrahedral energy. Next, we have some relation. Tetrahedral energy is equals to 4 by 9 times of octahedral energy. Similarly, for square planar, we can convert by multiplying with 1.3 into del O. Then del C is Q for cubic complexes. It is related with 8 by 9 into del O. We can write general term. For square planar, it has highest crystal field energy. Then for octahedral, then for del cubic, then for tetrahedral. So this is the order for different complexes energy. Next, we have spectrochemical series. So this is the general trend of spectrochemical series. This side we have pi donor ligands, and before H2O, all are weak field ligand. And after H2O, All are strong field ligand. Here CH3 minus and C6H5 minus is strong sigma donor. And after that PR3CN minus CO and NO are strong pi acceptor ligands. So this is the spectrochemical series. Based on this, we will decide weak field and strong field ligand. Then we have some important points like cobalt plus 3 shows low spin with iodide, bromide, chloride, fluoride, sulfide, SCN minus and N3 minus. These all are weak field ligand. So here pairing will occur when we fill the electrons in d orbitals. For octahedral complexes, if we have oxidation state greater or equals to 4, it will always show low spin. For 4D and 5D series, they also show always low spin complexes. If octahedral energy is directly proportional to charge on cation, if we have same number of d electrons, octahedral energy is inversely proportional to number of d electrons. If we have same oxidation state, if interelectronic repulsion is greater than CFSC energy, and that is greater than spin orbit coupling, the condition for weak field ligands. So firstly, electron will feel singling, that is high spin complexes, and in these complexes pairing energy is greater than octahedral splitting energy. This is the case for strong field ligand, and here pairing will occur and low spin complex will form here. In these cases, octahedral splitting energy is greater than pairing energy. Condition when interelectronic repulsion is almost equal to CFSC energy, that is greater than spin orbit coupling. Then here spin crossover phenomena will occur. Then last and fourth one is when spin orbit coupling is greater than CFSC energy, that is also greater than interelectronic repulsion. This is the case for lanthanoids and actinoids. Here this side weak field ligands, this side is strong field ligands, and this barrier is spin cross line. In this case dq towards strong field ligands increases and towards weak field ligand decreases.